Okay. So first of all, I will introduce the workshop and
Okay.
then you can share your screen. And good morning, everyone. Thank you so much for your interest in our workshop and for your active participation to our workshop. And first of all, we kindly ask you to update your Zoom participant name to your real name and surname. And we would like to thank our lecturers, Feyza Yavuz and Adnan Hardoğan, for accepting our invitation. In this session, our lecturer, Feyza, will talk about PyTorch library and PyTorch workflow. We wish you a nice and productive event. And I will briefly introduce dear Feyza Yavuz and leave the screen to her. And I would like to remind you all that the sessions will be recorded. Feyza Yavuz is a graduate student and teaching assistant at Middle East Technical University, is specializing in development machine learning solutions, particularly in deep learning. Over the past 3 years, her focus has been on various computer vision challenges, including object detection, efficient implementation of ranking-based loss functions, and energy prediction for urban scale buildings. Additionally, she has been a teaching assistant for data structures and computer networking courses for 4 semesters. So, dear Feyza, screen is yours.
Thank you for this kind invitation. Let me share my screen. And let's start with our session. Welcome to our session, first of all. My name is Feyza Yavuz, and currently I'm a master's student in Middle East Technical University. And today we'll make an introduction to a PyTorch library. And we will cover the properties of PyTorch, the data types, operations, the differentiation in autograd and neural networks. And finally, we will see some examples on Google Colab to understand PyTorch better. And let's start with our introduction. And PyTorch is actually one of the most popular open source deep learning frameworks. And it's developed by researchers at Meta, Facebook AI in 2016. And basically, it's a Python-based scientific computing package. And its main purposes are efficient CPU, GPU accelerated backend combining with Python frontend. So this allows us to express our deep learning models or any scientific calculation actually in Python. And as you all know, most of the data scientists are actually familiar with Python. So PyTorch stayed within this ecosystem to keep the interfaces simple and consistent. And actually, PyTorch provides excellent abstraction, which means that it hid the complex parts of machine learning process behind the APIs, such as the deep learning primitives, layer types, or etc. And we only need to write a few lines of code to make complex computations. And in PyTorch, we can manually control the execution process, and it's slightly incomplete. And by meaning incomplete, actually, I am talking about it's easy to implement or adopt new features in PyTorch, and this makes PyTorch very flexible. And PyTorch applies a graph metaprogramming based approach, so we can implement any neural network architecture with it. And we basically make our custom neural networks with PyTorch. And if we have to talk about the performance of PyTorch, the main core is to implement a tensor data structure both on CPU and GPU operations, basic parallel primitives, and automatic differentiation calculations. And the intensity level operations for this computation is actually written in C++, and C++ is very high performance programming language. So actually, the control flow in PyTorch is in Python, but inside of it can be expressed and optimized in C++ code. So why we are interested in PyTorch in deep learning community? One of the most important properties of PyTorch is its Python support. because Python is very readable and easy to understand programming language. And also we can combine PyTorch with different popular libraries such as NumPy, SciPy, or even Python. And we can use PyTorch for efficient debugging in Python. As you all know, we are having a really sophisticated tools for Python debugging. And the other aspect of is this Torch script. Torch script is about production environments in our applications or maybe even in our web applications. And Torch script provides a functional and flexible environment for production with PyTorch. And we can say that PyTorch enables the dynamic graph computation, which means it lets us to change the network behavior on the fly, and we do not need to wait all of the code to be executed. And another primary property of PyTorch is most of its rivals, such as TensorFlow, its automatic differentiation, and we say that this is used in training neural networks, and it basically computes the derivative of a function by making a chain of backward passes in neural networks. And we can continue with another properties such as scalability and in production phase. Using PyTorch offers scalability on cloud platforms, and it supports a variety of processing such as CPU, GPU, or parallel processing. And we can write our own computations, or we can use PyTorch app, which is a repository for pre-trained models, and it has a large collection of tools and libraries available. And our PyTorch community is also important. PyTorch community provides a detailed documentation and tutorials, such as video or written documentation. It has a lot of code examples, and also it has a lot of active forum for question and answering part. And before starting, I would like to remind you that you can download PyTorch from this link, pytorch.org, and you can follow the instructions such as which operating system you are using, Linux or Mac or Windows, or which package provider you are using, Conda or pip. And you should follow the instructors from here, but today it's not necessary since we are using Google Colab. And now let's start with the tensors. And PyTorch is fundamentally a library for programming with tensors, which is a building blocks for neural networks. And tensors are specialized data structures that are very similar to arrays and matrices. Basically, we can say tensors are just multidimensional arrays with a sophisticated name. And in PyTorch, we use tensors to define the inputs and outputs of a model, or define the model parameters. And they are very similar to NumPy's arrays, except that the tensors can run on GPU structures. And let me remind you the terminology. For one-dimensional arrays, we use the word vector. For two-dimensional, we use matrix. And for multidimensional arrays, we use tensors. And in PyTorch, actually, we can initialize the tensors in various ways. And one of the most simplest ways, actually, is to create a tensor with the torch.empty call. And you can see the syntax in here. And with this call, actually, we create a tensor X, which is a two-dimensional tensor. It has 3 rows and 4 columns. And here we do not define any types here, such as integer, float, or Boolean, since with this selection, actually in default, PyTorch tensors are 32 with floating numbers. Please keep in mind that. And torch.empty actually did not initialize any values for its tensors. It actually only allocates the memory for the tensor. But most of the time, we need to initialize our tensor with some values. And the most common cases are we need to start with all zero values or all ones, or maybe we need some random values sometimes for our computation. And Torch module actually provides all of these methods for these three cases. And for example, torch.zeros actually creates a tensor with full of zero values in it. In this example, you can see that this zero matrix or zero tensor will be a two-row, three-column tensor with all zero values. And here, torch.one similarly produces a tensor with full of values of one with the same shape. And this torch.rand function will generate a tensor with random values between 0 and 1. And please take attention to this line, torch.manual seed. We will talk about on this next time. Most times, actually, we need random value tensors. For example, we want to train a neural network model, and in the beginning, our model's learning weights should start from a random value. So we have to initialize some random values, but since we have to reproduce the same performance for each run, we have to produce the same random values each of the execution time. So torch.manual seed actually exactly does this. It manually sets our random number generator, and we achieve the same random number every time we run torch.rand. And let's continue with the other attribution of tensors, which are shape. And most of the cases, we need to have same shape tensors in order to make some operations with them. And for example, sometimes we need to add two tensors together or subtract two tensors together. And to initialize a tensor with the same shape as another tensor, we actually use torch._like methods, such as empty-like, zeros-like, ones-like, or rand-like. Actually, these methods works just like torch.empty, zeros, ones, or random, but with its parameter, we actually give these methods a specified shape. So they define, for example, in zeros-like, they create a tensor with the same shape as another tensor, which is filled with zeros, or in ones-like, the same operation with fills with one values. And in addition to all these, we can actually specify the data type of the tensor. I'm sorry, not the data type. Yeah, we cannot actually specify the data type, but we can also specify the actual data. And torch.tensor is the most straightforward way to create this tensor if we already have data. And keep in mind that the torch tensor creates a copy of the data, it does not overwrite the actual data. And most of the times, for example, in NLP problems or in machine learning problems that we have to extract data from CSV files, our data stored in NumPy arrays or pandas data frames. So we have to convert these data types to tensors using torch.tensor in order to use in PyTorch and our models. And this method actually takes two arguments. The first one is the numerical data, and the second one is the desired data type. And we can define several data types using such as .float, .long, or we can use the tensor-specific data types such as float tensor, long tensor, or overall tensor. By the way, tensor.tensor is a generic name for 32-bit float tensors. Or we can use .to function to initialize its specific data types. And we are actually having a lot of data types such as Boolean, integer, or unsigned integer, or float, double, etc. And I would like to explain another great function for creating tensors, which is called torch.arrange. And this function actually returns a one-dimensional tensor with elements ranging 0 to n-1. And we can also decide the starting or ending value or its step size. For example, in this example, we are using torch arrange with the value 25, which defines actually in this example, it does not return the 1D tensor because of this view function. But basically, we are having all values ranging from 0 to 24. And if we, for example, define the step as 2, then we will have 0, 2, 4, 6, 8, up until the 24. And once we create a tensor, it will have 3 main attributes: its shape, the dimensionality of the tensor, its data type, float, integer, or Boolean, etc., and its device, whether it will be stored on CPU or GPU. And we will talk about this device later. We should now see how can we manipulate the shape of a tensor. We can get the size of a particular dimension with the size methods. For example, this line actually gets the size of the 0 dimension, which means actually the row dimension. 0 means the row dimension. Or we can change the shape of a tensor with view methods. For example, we already saw that in this example. Actually, torch.arrange gives us a 1D tensor, and we reshape them or view them as a 5-row, 5-column tensor like this. And you should keep in mind that, for example, when we initialize xView as x.view from x.view, xView and x shares the same memory. So if we change one element or make an operation of one element on x, it will change the xView and vice versa. And we can also use torch.reshape for the similar purpose. And actually, most of the time, we are using torch.reshape. And we do not have to just stick with the given shapes. We can use squeeze or unsqueeze methods for adding or removing a dimension. And actually, unsqueeze function adds a dimension of size 1, just like in here. If we have 3-row, 3-column tensor, if we have an unsqueeze operation, then we have an additional 1 dimension in beginning of the tensor. And likewise, we can use torch squeeze to remove the additional dimension. This is 2D, this is 3D, and we can use squeeze to convert this 3D tensor to 2D tensor. And finally, if we want to actually the total number of elements in a tensor, we can use the numel method. And then, for example, in this tensor, if we call the numel method, it will return us 0. It will return us 9, sorry. And there are actually plenty of methods for manipulating the shape of or data type of the tensor, such as flatten. For example, flatten converts the multidimensional tensor into one-dimensional tensor. But today we are talking in introduction level, so these are the basic ones. And now let's see some examples of these functions using Google Colab. Can you see my screen now in Google Colab?
Yes, it's perfect.
Okay. Now we will make some basic operation on PyTorch tensors. We already talked about that the tensors are the central data abstraction in PyTorch. We are actually wrapping every data in tensors. And let's import the PyTorch module. And we are using import torch. We will run our cells. And please keep in mind that you can use these IPython notebooks. This is called an IPython notebook in Google Colab. You can use these IPython notebooks on Turubaz Slurmbetics. You can use them on using Slurm in our servers. And now we will continue to our examples. Let's start with the torch empty call. I will run them like from here. And you can see that now we create a torch tensor, which is by default a float tensor. We already talked about this. And you can see that there are a lot of weird numbers here because this is not initialized, they're only allocation. So you see whatever was memory at that time during allocation. So actually with this initialization, we create an X tensor with 3 rows and 4 columns, and each of the cells are typed with 32-bit floating numbers. And let's continue with some examples about zeros and ones. When I run this cell, I can see that the zeros tensor is actually a 2-row, 3-column tensor with all of the 0 values in it. And for ones tensor, we have seen the same with the 1 values. And for torch.rand, we see 6 different values, which are all range between 0 and 1. And speaking of these random tensors, we already talked about this manual seed on theory. Now we can see the actual practical work about the manual seed. For example, when I run this cell, let's run it, you see that in the first initialization, which is random 1, we are using the manual seed, and in the random 3, we are using the same manual seed, but in random 2, we are not using any manual seeds. So in this printing cell, we see that the first tensor and the second tensor are the same because they are using the same seed. But if we actually have it did not any manual seed, we are getting totally different values. This is very important in machine learning and deep learning approaches because if you did not define any manual seed, for example, you are achieving some very impressive performance in one random value, but you will never be able to get that performance again because you cannot achieve that the same random number generator. And continuing with the tensor shapes. Now, in first line, we initialize an empty tensor with shape 2 to 3. And if we using the empty-like function and given x as a parameter, then actually we are having this tensor, which is the same shape. I'm printing its shape like this in here. We see that we have the same shape actually. And when I print the empty-like, you can see that our values are different from x because we are not copying the x, we are only copying its shape. So it's important to know that. And when I continue with the zeros like, I can see that again, we are having the same shape. With ones like, I'm still having the same shape because I'm giving the axis shape. But the only difference is that with zeros like, ones like, and rand like, we are actually calling the zeros, ones, and rand functions with the given shape. So in these examples, I will have a tensor width full of zeros, tensor width full of ones, and tensor width full of random values. Actually, these using dot shape property, you can verify the tensor shape, and this is actually very functional debugging methods I am using all the time while working on some deep learning architectures, because we have to have a same shape, and we will talk more about this later actually. Now we will continue with how can we actually use data directly to create a tensor. Let's say that we have a 2-dimensional array. We can directly define a tensor using like this, or like this, or like this. Let's keep in mind them. This is a tuple in Python. And if we run this, we are using tuple as an input, but we are now having a 1D tensor. And if we have one tuple or one array, now we will have two-dimensional tensor, like 2, 4, 6 and 3, 6, 9. This does not change any of the semantic on tensor-like or tensor-wise implementation. And you can actually use pandas data frames or NumPy arrays, but these examples are not available in here. And most of the time, actually, we are importing some data from another files, such as TXT files or CSV files. And continuing with the data types, we are talking about shapes, we are talking about constants, and let's talk about the tensor data types. For example, when I run this cell, I can see that if I define a two-dimensional tensor, which is full with ones, and when I specify its data type with torch.integer, I actually have an integer typed multidimensional tensor. And when I print this, you can see that we do not have any dots next to these numbers, because in Python, when we define a float number, we have 1 dot 0 next to it by default by defining the integers to floats. But since we are using the integers, we are actually have only 1 values. So we can also define a bigger float as a data type. Recall that the default type is float 32 bits. So we can have bigger floats or we can have bigger integers, as you can see from here. And when you're printing a tensor, you can actually see its data type, and actually you can see its device too, but in Colab, we are not going into detail about now. And you can see a small example in here to how can I convert this tensor to integer tensor. For example, in these B tensor, we have values like this. And when I use b.to torch.int, actually now my tensor values will be rounded to integer values 10, 2, 19, 0, 1, and 5. And you have to take care about where to round these numbers. So please keep in mind that. And we are available data types. We already see them in our slides, but Boolean, 8-bit integers, 8-bit unsigned integers, 16 bits, 32 bits, 64 bits. We have half data type, float data type, double data type, and etc. And now actually we can continue with the operations. Now we know how to create a tensor, but what can we do about them? Actually, there are more than 300 operations available on PyTorch for both arithmetic, linear algebra, matrix multiplication, or even tensor manipulation. And in basics, we have to understand how can we reach data in tensor, like indexing or sliding. Actually, in PyTorch, we use NumPy-like indexing and sliding. If you're familiar with NumPy, this will be easy for you. And we can index on multiple dimension. We can index or single elements, or we can even access an arbitrary elements in each dimension. And for example, let's say we have 3-dimensional tensor. This will get the top left element of each element in our first dimension with our tensor. And these PyTorch operations for basic arithmetic operations are very similar to the NumPy, and we can work with both scalars or other tensors. We can add or multiply 2 tensors or 3 tensors together, or maybe more tensors. And for example, x plus 2, let's say x is a tensor, performs element-wise addition, and the arithmetic operation between these tensors and scalars are distributed over every element of a tensor. And if we want to apply these basic arithmetic operations on tensors, we need to have the same shape of different tensors. For example, let's say we want to apply a binary operation on tensors. They have to be an identical shape. And for example, if we have two-dimensional two tensors, we can make an addition or subtraction or multiplication or division between them. But if we have one two-dimensional and another two-dimensional tensor with different row size or different column size, we cannot perform any binary operation on tensors with these shapes. And our code actually will throw a runtime error, and the text of this runtime error we can see as the size of tensor A must match the size of tensor B at non-singleton dimension. This is actually the error that we will see in our Google Colab examples. But there are a lot of actually exceptions to this same shape rule. And this is called as tensor broadcasting. And broadcasting is a way to perform an operation between tensors that have similarities in their shapes, but they are not identical. And the rules for this broadcasting are, the first one is that each tensor must have at least one dimension. We cannot apply any operation on empty tensors. And from last to first, we have to compare the dimension size of these two tensors. And there are three possible size comparisons. First one is that the dimensions are equal. The second one is one of the dimensions must be size 1. And third one, the dimension does not exist on one of these tensors. For example, we have an image. Image is an 3 times height times width times tensors. If we have another tensor, which is, for example, grayscale, which means height times width shape tensor, we can apply it to our image as a filter, but we cannot apply 4 times height times width times tensor to our original image tensor. And we will have some examples on this on our Google Colab example slide. And we can continue with matrix multiplication, because in most of the scientific computing or deep learning, we are actually making a lot of matrix multiplication. And we can use tensor.matmul methods for matrix multiplication. And we can also actually perform with this symbol, but for readability, I suggest you to use tensor.matmul. And we can take the transpose of a tensor for tensor.t. Actually, this is another hidden attribute of tensors. You can get transpose of any tensor at all one time. Let's see here, we have a 1D tensor. We can reshape it to 3 times 3. Then if we take a transpose, we see that all of the rows become columns. And actually, we say that we have a lot of operations. We can take mean and standard deviation, both in overall tensor or along with a certain dimension. We can call these methods with no parameter to whole tensor. And for specific dimension, such as rows and columns, we have to give parameter for the given dimension. For example, if we have this tensor, which is full of 1s, 2s, 3s, and 4s, if we have the overall mean, we have the overall mean of these values, which is 2 times 2.5. And if we only want to have the mean in row-wise columns, we have 1, 2, 3, 4, which total 10. We divide it by 4, 2.5, 2.5. And if we use the first dimension, we will have the means of these values, which is 1, which is 2, which is 3, and which is 4. And to use mean and standard deviation in our tensor should be a floating point type. And this is one of the many errors and runtime errors caused by our codes. Please keep in mind that. And we can also use concatenation of some tensors, which is actually crucial for our deep learning operations because we are actually making concatenated tensors along with the deep learning architectures. And let's go from an example. Let's say we have an initial tensor called A, and A has, this is A, 4 times 3 tensor, and its initial size is 4 to 3. Then let's say we are concatenating this like A on dimension 0, which actually causes to stack all of the A's, all 3 A's by row wise. So now we have 12 rows and 3 columns. And if we want to do concatenation on dimension 1, which means we actually stack these A tensors on column wise. So now we have actually 9 columns and 4 rows. And the important aspect of these operations are they are not in place actually. So for example, if we are using, let's say, torch cat AAA dimension 0, if we did not initialize to another variable called, for example, A underscore cat 0, we actually did not reach any time this operation and the result of this operation. So we have to, if we want to update the value of A, we have to add A equals to A dot A. And to have the updated values. And PyTorch offers the in-place versions of operations by adding an underscore. So if we use, for example, the add or multiplication or subtraction with an underscore, now we do not have to use A equals to A dot A to have the updated values. This will make the update itself. And this is an important one. Now we will talk about how can we copy these tensors. Like actually in Python, we have to copy, we have to copy a value to use it another place. So assigning a tensor to a variable actually makes the variable like a label of a tensor and does not actually copy it. So remember that we say that if we use the view function, we have xView equals x.view, and if we change any value on x, then it will change any value on xView. So actually, this is not something that we want, so we have to separate the copy of the data, and we can use the clone method for this. And we have some examples, I suppose, on Google Colab. And let's talk about, before the break, let's talk about how can we move this on GPU. We say that one of the main advantages of PyTorch and tensors, actually, it's robust acceleration on CUDA-compatible NVIDIA GPUs. But how do we move our work to a faster hardware? First, actually, we need to check whether or not we have an available GPU using torch.cuda.isAvailable methods. In our computer, we are not always having a proper GPU, so this is a crucial method in order to have a running environment. So if we have available GPU, we actually need to put our data to somewhere where the GPU can actually see it, because our CPUs in our computers does the computation on data in random access memory, and GPU has another dedicated memory which is attached to it. So you must move all the data needed for computation to a GPU memory accessible. And there are multiple ways actually. You can do it at creation in torch.tensor by defining a device parameter. And by default, our tensors are float typed and our tensors are created on CPU. So if you have an existing tensor, you can actually move it to another device such as GPU or CPU by using .to CUDA. This is a string parameter. This is for moving data to GPU, and or to.cpu method, and this is for moving data to the CPU device. So one of the important aspects, recall that if we have a computation involving two or more tensors, we say that they are at least have similar or same shape. And in addition to that, they should be also on the same device. So if you have one tensor on CPU and one tensor on GPU, you cannot actually add or subtract or multiplicate or do any operations involving these two tensors. So you have to move one of the tensors or the another tensor into the same device. So actually, let's start with the mathematical operations in Google Colab. Then we will have a question and answering session. Then we will have break. And let's say the basic primitive operations in PyTorch. Let's say we have a zero initialized tensor with 2 rows and 2 columns. And if we add 1 to them, we can see all of the cells increased by 1. And let's say we have a tensor with full of 1s, again with the same shape. If we multiply them with 2, now we can see that all of the elements should increase by 2, multiplied by 2 actually. And in this tensor, actually we can see that we can chain this basic mathematical operations just like in basic Python or in our mathematics classes. So please don't forget, have an additional care for these chained arithmetic operations. And there are another examples such as 2 to the power of 2, which causes and taking a power on each cell or taking the square root of the each cell. And we can also use these basic operations on with multiple tensors. For example, we can run these power tensor in this 2's tensor. 2's tensor is actually this tensor, 2, 2, 2, 2. And if we take power with this tensor, which is 1, 2, 3, and 4, we see that in first element, we are having the first power of the 2, the second power of the 2, the third power, and the fourth power of the 2. And we can also add 2 tensors together like this. You can see the 1 tensor and the 4 tensor. We can add them. It adds each element at the same position. So we are seeing all elements are the same, but this is work like this. Actually, 1s are here, 4s are here. It has 1, 4, 1, 4, 1, 4, and 1, 4. And we can actually use multiplication. And please keep in mind that these tensors have the identical shape. They all have 2 rows and 2 columns. So what happens when we try to perform a binary operation, which is addition or subtraction or multiplication actually on tensors with the similar shape? We say that it throws a runtime error. We can see this error actually. Let's say we have a random tensor with 2 rows and 3 columns, and another random tensor B, which is 3 rows and 2 columns. If we try to multiplicate these 2 tensors, we will have a runtime error, which is the size of a tensor A, which is in the same row, must match the size of a tensor B. Actually, it gives at the first dimension, not the 0 dimension, at singleton dimension 1, you can see the A's first dimension is 3 and B's first dimension is 2. The 0 dimensions are rows 3 and 2 or 3. But we talked about the tensor broadcasting for how can we use workaround about this with similar shaped tensors. Let's say we have two row, four column random tensor, and if we have one row, four column tensor multiplied by two, actually this is now can be available for binary operations operating on rand tensor. Let's say we see the random tensor here, and you can see that this tensor actually is one row with four columns and each cell has twos in it. So we see that for all elements in this random tensor, we actually multiply it by two by this multiplication. So how we got a multiplication with a 2 to 4 tensor by a 1 to 4 tensor. And we say that in our slides, we say that each dimension must be equal, or one of the dimensions must be the size of 1, or the dimension does not exist. And in this case, our actually example falls in this category because our second tensor has dimension 1 on its row in its row dimension. So we can actually broadcast these tensor with our random tensor, and we can apply multiplication or addition or subtractions. So actually there are a lot of examples that we can work with as a broadcastable tensors. Let's say A has a three-dimensional A is three-dimensional tensor with all one values. We can actually multiply with this tensor because the first dimension is absent, which takes into this category. The dimension does not exist on one of the tensors, and the other dimensions are same with the A tensor. So actually we can multiply A tensor with this tensor and obtain B here. This is the B tensor. And another example, we can actually use this tensor, again, to be able to multiplicate with A. You can see that the third dimension is 1, which is another category of our broadcastable tensors. And the second dimension is same to the A second dimension, and the first dimension is actually absent. And the third example is another example. You can see the last dimensions are same. The second dimension is 1 in this tensor, and the first dimension are again absent, and we can actually multiplicate these. These examples can be seen a little complicated because we are using the random values, so all of these values in these cells are full of random, but you can analyze this. If you want, I can share this IPython notebooks with you, so you can analyze it in more detail. And let's see another example which throws a runtime error. You see that we talked about these categories in here, in above. We are going from last to first. So in here, we have an absent dimension, but since we are going from last to first, this is not a problem for us. But in here, we are having a runtime error because in the last dimensions, these are not falling of any of these three categories that we are discussed before. So we cannot multiply our A tensor with this random tensor. Actually, dimensions must match last to first. And in our second example, actually Python uses a lazy evaluation. So in here, we are gaining an runtime error, so we cannot even compile or run these lines, but I will talk about them again. You can see both of the third and second dimensions are different. So again, we cannot multiply A with this tensor, and we cannot multiply our tensor with an empty tensor. So finally, I can give some examples about the operations in tensors. Let's talk about them. Actually, we can have the abstract function, which gives the abstract value of A. For example, let's say A is this tensor. So if we use the, I'm sorry, not abstract, absolute. So if we use torch.abs, we will obtain this. And if we have, for example, ceiling operation, which rounds the value to the biggest value smaller than A in each element. Now, for example, sorry, I got complicated. Ceil is the upper value and floor is the lower value. So ceil gives the smallest number bigger than A, and floor gives the biggest number smaller than A. So we can also round with the given step sizes, start and end, and we actually using clamp function to squeeze our tensor to given these values. And we are also have trigonometric function and their inverses. We can use sinus, cosinus, or asine. This is the inverse of sinus function. And we can also have bitwise XOR operations. We can make some element-wise equality comparison. For example, we can compare two tensors, each element, does it equals or not? Or we can use some reductions, gives, for example, maximum value returns a single element in a tensor, which has the maximum value. And you can use these dot item method, which let's say torch.max gives as a single element tensor. It still return us a tensor. But if we use torch.max.item, then we have the extracted value such as float or integer directly from this tensor. And now with these .item, we are no longer working with actually tensors. Now we have scalar values. And we can have mean, standard deviation, product of all numbers, and we can actually use torch.unique to give all of the unique values in unique elements. For example, this line should work and return 1 and 2 to us, like in here. I cannot see, 1 and 2 tensor. These are the unique values in our example tensor. And we can actually define some linear algebra definitions such as x unit vector, y unit vector, and we talked about this random operation, and we can actually define an identity matrix, which is very important in our scientific computing researches. And we can compute again cross product, matrix multiplication, or singular value decomposition. So actually, there are one last operation that we have to talk about, which is the in place. Let's say we have a tensor like this. This is a complicated tensor. We have in here, and we have the, let's say we call the torch.sinus function. We can see that we can print the values, but again, when we call the A tensor, we see that the values of A are not updated. So if we use the underscored version of the sinus function, actually now we are having the updated values while printing B again. So if we have to get the updated values, we can use these in place operations, which is basically a method and an underscore value with it. So actually there are a lot of examples such as add in place operator, multiplicate in place operator, and these are all works the same as this sinus example. And actually these are, we talked about these, we talked about copying tensors. You can analyze it if you want. And actually, before the break, that's all I want to talk about. If you have any questions, I can actually take them right now. So I suppose there are no questions. Ah, are you going to share collab files? Actually, yes, if you want to have an access to them, I can share it from, I think, from the,
Yes, we can upload the presentation files and also notebook files to our events webpage, so you can
okay,
check the webpage for updates.
okay. So there is another question on chat. For example, if we run torch.random 2 times after setting a seed, do we get the same 2 vectors all the time? Actually, yes. Are you talking about like, let me find the parts here. We are talking about empty zeros. So you are talking about, I suppose, if we set, I cannot see actually the socket. Okay. If we run torch.random 2 times after setting a seed, do we get the same 2 vectors? So you are actually asking this. We have setting a manual seed, then we call torch.random, then we have another torch.random. So no, we do not have the same values because these random does not have a manual seed. If we want to have the same random values, we need to set our manual seed to the same value before we call the random function. There are, I suppose, another questions in Q&A. Did you have any experience on complex numbers with tensors? Actually, I did not have any experience, I suppose, maybe in one of the courses I took, because I'm working on actually image data. So there's no need to work on complex numbers with my specific working area. And that's all. So I think there are no more questions. So let's have a break for 15 minutes. Then we will continue on differentiation and neural networks. Uh, we have a question actually, and let me answer it. Let's say we set seed and then call two random times and did this again. Do we have the same two vectors in these two times? If we define the manual seed before each random calling, then we will have the same two vectors. But if we do not define the manual seed for each random, then we shouldn't get the same values. So think of it as the random function actually generates a random number generator. So by using manual seed, we are saying to our code that use the same random number generator. So if we want to have the same vectors by calling the random two times, we have to define two times the manual seed line. Is it okay? Then again, actually, no, we are calling that random one time for each seed setting. So if we have one seed setting and two random calls, then we will have different random values. Okay, sorry. So if you say that we have a manual seed setting, then we call random two times, then we have another seed setting, then we have two random calls, right? The first random and the third random will have the same random values if we set the manual seed same, and actually the second and fourth ones have different values than the first one and third one. You're welcome. And evet, 1 ve 3, 2 ve 4 için aynı çıkacak. 1 ve 3'te manual seed şey yapıyor olacak. E, doğrudan mesaj olarak gelmiş ama yine de buradan cevaplayayım. E, bahsettiğin setup'ta manual seed'i define ettiklerin aynı çıkacak. 2 ve 4 de aynı çıkacak ama 1 ve 3'ten farklı olarak çıkacak. Bunu aslında sen PyTorch'un kendi dokümantasyonunda da görebilirsin. Yani 2 ve 4 1 ve 3'ten farklı çıkacak anlamında dedim. Yani 1 3 aynı, 2 4 aynı çıkacak gibi bir şey olacak orada. Ee, PyTorch'un kendi sitesindeki dokümantasyonlarında daha detaylı ve böyle daha farklı örnekler oluyor. Ben burada giriş seviyesinde olduğumuz için hani bu tarz örnekleri eklemedim. Şimdi devam edeyim olmadı derse ben. Welcome back again. Now we will talk about, in this part, automatic differentiation and data sets and data loaders. Then we will actually talk about our basic neural network models. So actually PyTorch, TensorFlow, and other machine learning libraries are known for their automatic differentiation feature. And you can all hear me or see the screen, right? Correctly? I suppose there are no problems. Okay. Okay, so PyTorch actually adopted a chainer innovation called reverse mode automatic differentiation. You can recall this by thinking about the chain rule in taking derivatives, because we are having a chain of linear or nonlinear operations in our deep learning or machine learning models. So when we want to take the derivative of the output with respect to the input, we have to actually call a lot of chain reactions, a lot of chain rules or chain derivatives to calculate the given derivative. So essentially, actually, it's like a tape recorder that records completed operations and then replaced backward to compute gradients, which we call the backward method, to ask PyTorch to calculate its gradients, and we store them in a grad attribute in Tensor. So let's take it on full screen and let's have an example. Let's say we only have a one-valued tensor called x, and we define its requires grad parameter to true to tell PyTorch, let's store its gradients. So if we define a function called y, which is actually 3 times 2 to the power of x, and we want to backwards of y, and when we take the derivative of y with respect to x, which is actually 6 times x, we see that x dot grad, the grad attribute of the x tensor, will be 12. So let's run a backpropagation from or backward from a different tensor to see what happens. Let's have another function which is the same value as y, but we define it as a different variable, which is z, and we call the backward on z. Now we can see that we have a grad value of x, which is 24. So we can actually see that the x's gradient value is updated to be some of the gradients we calculated so far. 12 comes from here, 12 comes from here, there, and when we print the overall gradient value of x, we actually see the value of 24. So we are talking about the machine learning perspective of AutoGrad. And a machine learning model is actually a function with its inputs and its outputs. So in machine learning, actually, our interest for talking about outputs will be the model's loss, since we are making a training. And since we want to minimize this loss, we are actually taking its first derivative with respect to the input and make it equal to 0. But we cannot directly calculate this loss from the input, since we are having a lot of function or linear activations in the middle of this function. So this derivative contains a lot of chain rules. So in our models, we are actually having a lot of partial derivatives of the model's output with respect to its inputs. Because let's say we have an input value x, we are making a linear transformation 3 times to have an output. So if we want to take the derivative with respect to the input, we actually have the first derivative according to the last linear layer, then another derivative according to the second linear layer, and another derivative and another derivative. So the full expression for each partial derivative is actually the sum of the products of the local gradients or local layers. And in simpler words, actually the gradients over the learning rates. So when we run a backprop in a neural network, we actually sum up all the gradients for a particular neuron before making an update. So in every training iteration, in order to have correct gradients, we actually have to run zero grad. So otherwise, our gradients would actually summing up for each training iteration to the other, which would cause our updates to be wrong. So we have to talk about detach method in here. So if we remember the torch.tensor, which is our actually main method to construct a tensor, and torch tensor actually constructs these tensors with no autograd history, nor requires grad attributes. So in difference to the torch tensor, torch clone actually creates a copy of tensor that imitates the original tensors, requires grad fields. So let's say if we have the tensor x here, and we are calling the x torch.clone x, we are actually having the same value for requires grad attribute while using torch clone. So if we want to remove this tensor from our computation graph, which is backward chains, we need to use detach. Let's have an example. In the left side, we are having the same function without detach, and the right side we are having with detach. And let's say we have a tensor which requires grad called x, and the y and z values are x to the power of 2, and our result, let's say, defined as y plus z and overall sum, because this overall sum comes from, since we are having a 28 times 28 matrix, the overall sum. So when we look at the backward history of this function, we can see that in here we have summation backward, in here we have addition backward, and now we have 2 powers backward for both y and z to reach to the x. And in the right side, we defined z with x dot detach. So in our backward graph, we have, similar to the left side, the summation backward, the addition backward, but now we are only having the power backward for y. We are not taking these backward calculations from now on, and then we are reaching x. Before going into detail about datasets and data loaders, we can actually work on some details on autograd. Let's say this is the explanation part of autograd, and you can read it from the collab file. And let's say import what we need, torch and matplotlib. Then we should create an input tensor full of evenly spaced values on an interval 0 to 2 pi and specify requires grad true. How can we achieve this? Actually, we can achieve it using torch.linear space function, and it actually accepts an optional requires grad option like here. So we are setting this flag, and means that in every computation that follows, autograd with accumulating the history of the computation in the output tensors of that computation. So let's say we define an A, which is a linear space tensor. Then we print A, we see that our tensor like this, and it has a requires grad attribute. Next, we will perform a computation by taking a sine function of A and setting it to B. Let's replot it by detaching it, of course, and we see this is our actually be the sine function of A. This is the plot of sine function of A. And the values of the sine function is stored in B. So you can see that when we print the B tensor, we see an indicator that is tracking its computation history with sign backward. So this gives us grad fn, gives us a hint that when we execute the backpropagation step and we compute gradients, we'll need to compute the derivative of sine x for all of the tensor's inputs. So let's perform some more calculations. Let's define C, 2 times B, and D, C plus 1. And you can see that for C, we have grad fn called multiplication backward, and for D, we have addition backward. So let's compute a single element output, and we can work on an example. When you call backward on a tensor with no arguments, it expects the calling tensor to contain only a single element. As in a case, like in our machine learning models, we are computing a loss function. Let's say the output tensor will be summation of all elements in D tensor, which is 25. And you can see that its grad fn is sum backward. So we see that each grad fn stored with our tensors allows us to walk the computation all the way back to its inputs with the next function's property. So we can see below in these examples, we can, when we run it, we have the property on D for all of the prior tensors. And note that a.grad fn is reported as none, indicates that this was an input, since we have the overall input as A, because we generate C, B, and D from A. So when we look at these grad fn, we are having an add backward, then its next function, we have a multiplication backward, then its next function, we have sinus backward, and then we have accumulation backward. And for C, we actually have multiplication backward, and for B, we actually have sign backward. And for A, since it's input, we do not have any backward operations. And so how can we get the derivatives out? And we can call the backward method on the output, out.backward, and we can check the input's gradients property to inspect all of the gradients. So when we call the backward function from the outputs variable, then we can check the gradient values stored in the input variable, which is this tensor. And when we plot this, actually, according to A, we have like this computational graph. So we recall the computational steps to have a better understanding. Let's say A is a linear space input, B is the sign of this A, C is 2 times B, and D is C plus 1. So overall output is summation of D. So as you can see, adding a constant C plus 1, as we did to compute D, does not change the derivative. This leaves C equals to 2 times B equals 2 times sin A, the derivative of which could be 2 times cos A, which is this graph. So in here, in upward of our calculation, we see that B, which is the sinus of A, have this graphic, and we have the gradients 2 times cos A having this graphic. So how can we turn autograd off and on? And the simplest change is actually we are setting the requires grad flag true or false. And when we see that, let's run it. A is 2 row 3 column tensor with ones, and it has requires grad true. This is input. And B1 is 2 times A. When we print B, it has this grad fn, which is multiplication backward. And when we set a requires grad to false, we actually have another function 2 times a. And when we print it, we did not see any grad fn because now we are closing the grad computation to false. And now we do not have any additional flags to here. So if we only need to turn off autograd temporarily, a better way is to use Torch NoGrad. We actually used a lot of in our deep learning codes and works. So you can see we can use this with torch.nograd and with an indentation, just like in for loop or if in Python. And now C2 here did not have any grad fn. But below this with torch nograd and above this torch nograd, we will have these grad fn variables. So you can also override your methods or functions with @torch.nograd to define a function with actually no keeping tracking of these autograds. So there is also corresponding context manager, torch.enableGrad, for turning autograd on when it isn't already on. Let's say in here, you can actually define a function with nograd, and you can define an if case. Let's say there's a case, then you have to open your grad calculation like this, put blah, blah, blah. And else case, you did not want any gradient calculation. You can use like this. And finally, you may have a tensor that requires gradient tracking, but you also want a copy that does not. So for this, we actually have a detach method. We already talked about it in our slides. It creates a copy of tensor, which is detached from the computation history. You can see when we define an X tensor, which requires grad flag, we are having it here, but when we detach it, we do not have any related flags here. So there are some operations between autograd and in place, but I'm not talking about it today. I will continue with my slideshow on datasets and data loaders. So since we are using our machine learning models for a lot of chunky data, code for processing these data samples can get very messy and hard to maintain. We are actually having a lot of CSV files, a lot of image data. So we actually ideally want our dataset code to be decoupled from our model training code for better readability and modularity. Let's say we have some error for some input examples. We want to see which data, where is its location. So PyTorch actually provides 2 data primitives to achieve all this, which is a data loader and dataset, and it allows us to use preloaded or our own data. So dataset stores the samples and their corresponding labels, and data loader wraps an iterable around the dataset to enable easy access to the samples. So dataset actually stores these input examples or input data and their labels, and we are calling data loader as a wrapper into dataset to be able to reach all of the dataset in a sequential way, like a mini batch setup or a direct setup. So we can index datasets manually like a list. So PyTorch actually provides a number of preloaded datasets such as MNIST, Fashion MNIST, and which is a subclass of Torch utils data dataset. And it actually has some specific functions for specific datasets, so you can use them very easily. And we can also create a custom dataset classes for our own data. And most of the time, since we do not have work with generic data, we are also using some data from our specific projects. we have to implement these custom dataset classes. And to implement these custom dataset class, we must implement these three functions: init, len, and getItem. Actually, the init function is run once when we actually constructing the dataset object. You can think of it like a constructor. Then the len function actually returns the number of samples in our dataset, and the getItem function loads and returns the sample from dataset at the given index. Recall that we say that we can index datasets manually like a list for a given index. Actually, we are doing it by defining a getItem function. And let's continue with how can we build the network. I'm not showing some examples about building the dataset because the scope of this workshop. So let's continue with the neural networks. Actually, if you are familiar with the deep learning or machine learning, you know that neural networks actually have a lot of layers that perform operations on data sequentially. Let's say you have an input, then we have several convolution layers, max pooling layers, then we have fully connected layers and some activation functions between them to produce a meaningful output. So torch.nn, which corresponds for neural network namespace, provides all the building blocks. Actually, you need to build your own neural network. And every module in PyTorch actually subclasses the NN module. So if you want to write your own neural network, you have to actually make a subclass to the NN module. So a neural network is a module itself that consists in other modules or layers. Let's talk about the most simple layer, actually, a linear layer. And linear layer actually performs the operation A times X plus B. We call the linear algebra, where A and B are actually initialized randomly. So if we don't want to learn, if we don't want the linear layer to learn the bias parameters, we can initialize our layer with bias equals false. And the syntax in here, like nn.linear, h in and h out, which means the dimension of input and the dimension of output, which is the n, the number of inputs, arbitrary number of dimensions, which is a colored image. Now we have 3 dimensions, but in grayscale image we have 2 dimensions, and h in, which is the size of the image, for example, and the output of matrix, which is, for example, for MNIST, which we classify the digits, h out will be 10. So the star denotes that there could be arbitrary number of dimensions in between. But the important part is what we given as h in and h out. Let's say in left part, we define 2 inputs, h in, and 1 output h out. And actually, this means that we have 2 inputs with 2 weights to come to the one neuron, which has a bias V1, and we are actually making E1 times W1 plus E2 times W2 plus B1 equals to O1. And another example, we can have 3 inputs and 2 outputs. For each output, we have 2 neurons. Now we have 2 times 3, 6 weights, and 2 biases. This is actually a basic approach for defining a linear operation. And there are several other configured layers on the neural network module: convolutional layer, transposed convolutional layer, batch norm, or upsample or max pooling. There are different methods in deep learning. And we can treat each of these layers as plug and play components. We can order them, we can add some additional layers or remove some layers to have more or less, big or small network. And activation layers are, activation layers are used to actually adding a non-linearity to our network, which based on activation functions. We can use the NN module again to apply these activation functions as an activation layer, such as ReLU, sigmoid, or Liqui-ReLU. And these functions actually operate on each element separately, like an operation in our previous lecture. And the shape of the tensors we get as an output are the same as the one as we pass in. So we are actually, while we're calling an activation function on a tensor, we are applied to each element of the tensor separately. So let's continue with our example. Let's say we have a linear layer and then we have a sigmoid activation layer on top of it. So if we have the output E times W1 plus E2 times W2 plus B1, then we send it to as an input to our sigmoid activation layer, and the output of this sigmoid function will be our overall output. And here, let's say we have multiple outputs, such as O1, O2, and O3. When we have the sigmoid activation layer on top of this linear layer, now you see that for each neurons in here, for each output, we have actually a sigmoid function. We apply the sigmoid function each of the elements. So overall, actually, you see that we can create layers and pass the output of the previous layer to the input of the next layer. So instead of actually creating intermediate tensors and storing and passing them around, which is not a great way to write a code in deep learning, we can actually use NN.sequential. You can see here, we are wrapping our layers with NN.sequential. Let's say we have a linear layer with 2 inputs and 2 outputs. Then we have an activation layer. Then again, we have another linear layer, which have 2 inputs coming from here and 1 output. Then again, and another activation layer, sigmoid, we can have 1 output actually with 2 inputs and 1 output with 4 layers in between. And in left, you can see another example with 2 inputs and different shapes. Linear layer, 3 outputs, then sigmoid, then all of these 3 outputs will come into an input as another linear layer. Then we have overall output with an additional sigmoid function. So these layers actually can be called as custom layers. So we do not have to use these predefined models such as NN.linear, NN.sigmoid, or NN.ReLU actually. We can define our own linear layers or our own convolutional layers, ReLU, leaky ReLU. Maybe we actually define a brand new layer or brand new function, then we can convert it to layer with custom modules. We can build this by extending the NN.module class, and we can build new complex modules and such as custom neural network. So to create this custom module, the first thing we have to do is to extend the NN module. Then we can initialize our parameters in the init function. Recall that we have this in our data set and data loaders. This is like a construction, starting with a call to the init function of the superclass. And all of the class attributes we define, which are NN module objects, are treated as parameters, which we can learn during the training. And tensors are not parameters, but they can be turned into parameters if they're wrapped in NN.parameter class. I am not talking into detail and giving an example about it because in the next session, you will actually see how to create an MLP implementation. So you can talk about freely in here. So when we create a custom module or custom network, we actually have to implement a forward function where it is a tensor, an input tensor, to produce an output. And since we now define our model, we define our data set, we will be able to generate some outputs. But however, in machine learning, we are actually having an iterative process to learn the best distribution for our data. So sometimes we are having the gradients isn't enough for our models to learn. We have to apply the backpropagation to be able to adjust our model rates. So we actually show how the gradients are calculated with the backward function. So we also need to know how to update the parameters of our models with these backward functions. So PyTorch also has a module, torch.optim, which contains several optimizers. We have used SGD or Adam, which is one of the most popular optimizers. And they are also having a learning rate parameter, which determines how big of an update will be made in every step. So if we choose a large learning step, we can make big jumps between our gradients. So if we have small learning rate, we will have small but steady steps in our updating parameters. So different optimizers will have different hyperparameters, and you have to tune them in order to obtain your model's best performance. So after we have our optimization function, we can actually define the loss to see what we want to optimize for. We can either define the loss ourselves or one of the predefined function in PyTorch, which is binary classification, maybe softmax loss, or etc. And you can define your own loss functions according to your own problem. So here you can see the overall training loop in PyTorch. Let's say we have our data defined before this code block called xtrain and xtrain, y prediction, y ground truth labels. Let's say we pass the data through the model for a number of epochs. For example, let's say 100 or 50 or 3, 4, 5, how many epoch you want to define. We put our model in training mode. We make a forward pass on our trained data using actually forward method, which is located inside our model object. Let's remember that we say that while we are creating the custom modules, we have to implement a forward function because NN modules, predefined functions have already forward in it. So if we have a custom module, we have to implement a forward because we are actually obtaining the prediction values by using this forward method. Then we calculate the loss function, which is basically measures how different our model's predictions to the true values. Y true is the ground truth values, and predictions is the one that we are obtaining from our model. Then we have to zero the optimizer gradients with zero grad because they accumulate every epoch, zero them to start with fresh each forward pass. Then we perform backpropagation. You see that we have input xtrain. Then overall, we have a loss function, which is a singular value, as we talked about in theoric part of the autograd. Then we obtain a backward in loss, which is a singular. Then we step the optimizer, for example, Adam, to update our model's parameters with respect to the gradients calculated backward. So this is running in a for loop for each epoch, and naturally we are seeing a performance gain in our model by following this pipeline. So let's continue with our module example. We can say that we are, let's say, defining a tiny model which has init function and a forward function. This is a custom model. Let's say we have a linear layer, an activation layer as a ReLU, then another linear layer, and then a softmax as another layer. So when we want to write a forward function, we actually, at each step, setting the input of the previous, setting the output of the previous layer to the input of the next layer. So we are having the base input, then we apply it to the linear layer, then we apply the output of the linear layer to activation, the output of the activation to the another linear layer, then output of the softmax, and obtain the overall output. So we have defined this class called tiny model, which extends to NN module. And now we construct this like this. And you can see our model, when we print our tiny model, you can see that it has one linear, one activation, one linear, and one softmax. And you can see the input and output features, and you can see whether or not we are learning the bias factor. So if we want to print or see just one layer, we can actually, since this is its parameters, self.linear one or activation, we can actually reach them by calling tiny model.linear2 or activation or etc. And we see that just one layer, which in this example is linear2. And also we can see each model parameters by calling tiny model parameters and running a for loop in it. So our basic parameters are like this. You can see in here, this is just a bunch of random values at first. And again, you can see a specific layer parameters for defining tiny model.linear2.parameters and running a for loop in it. So in here, you can see the layer 2's parameters. So we have talked about the linear layer. Let's say we have a random input and a linear layer with 3 inputs and 2 outputs. Our input is this. Our parameters for weights, since we have 3 inputs and 2 outputs, we have 6 weights like here. And we have, for 2 outputs, we have 2 bias values. Then when we apply linear layer to the inputs, then we have 2 outputs, which is this, which is actually weight times input plus bias gives us this output. This is actually a matrix multiplication. So we have convolutional layers. I'm not talking about in detail because it's not a starter value for this course. So we can talk about, we already talked about the activation functions and loss functions, and you see the detailed analysis of how can you use these activation or loss functions in the next session. So actually, that's all for my session today. If you have any questions, I can answer them. And please recall that the next section is about how can you implement a multi-layer perceptron, which is a basic network, you can say, in PyTorch. Welcome.
Thank you very much for all the information that explains all the fundamental concepts very well. And I would like to thank her once again for her time and valuable contributions. Hope to see you in the afternoon sessions on MLP CNN implementation and training. Our session will start at 1:30 in Istanbul, Turkey time. So the Zoom session will stay open. So if you have any questions, please ask via Q&A box.
And I would like to make some comments about the session. Please recall that this is a very dense session for an introduction to PyTorch. While actually we are working with PyTorch library, we're actually obtaining various errors because of our implementation methods. So please refer to the official document of PyTorch. It has various of code examples, video tutorials, as well as IPython notebook examples. And also, actually, you can find any type of question like Stack Overflow in PyTorch's community page. I actually use it a lot, and I recommend it to you also.
I think we have no questions. So see you in the afternoon session.
Yes.
So, good afternoon, everyone. Welcome to the second session of Introduction to PyTorch Library Workshop. In this section, our lecturer, Adnan Harun Doğan, will cover the fundamentals of MLP, CNN implementation and training. And so before the introduction, we would like to thank him for accepting our invitation and his valuable contribution. Additionally, I would like to inform you that all the sessions will be recorded and the recordings will be available via EuroCC YouTube channel. I will send the links via chat. And allow me to introduce him briefly. Adnan Harun Doğan is a graduate student and teaching assistant at Middle East Technical University. He is working on incorporating increasing and decreasing combinatorial optimization algorithms into deep learning pipelines using implicit differentiation in image processing and pattern recognition lab, which is located in Middle East Technical University. So the screen is yours. So
thank you, Selin'cim. Hello again, everybody. You don't have any echo or something, right? Like before I restart, I had to check. Okay. Well, today we would like to start with two basic implementations of MLP and CNN models. The one task is a regression task where we want to predict a value, a continuous value, using a publicly available dataset from Kaggle. And in the second part of this presentation, we will go with a CNN architecture that classifies a well-known dataset that is called CIFAR10. As the basics and also the documentation and also architectural details are explained by Feyza Hoca previously, I would like to briefly just introduce the dataset and also make our hands dirty with the problem. Okay. But before we start, let me just quickly show you the dataset, how we can find this dataset, and also what we can do with that. This is this dataset is very basic. It has 8 columns in it, if you can see. I will try to show you in my notebook file, but I'm trying to find the yes. We can download this dataset from a Kaggle, and it should be publicly available. And also we can I will show you how to download it, and also I will share my script. As you see, we have many datasets from scikit-learn library, and I'd like to just
sorry for interrupting. If it's possible, could you please maximize the okay, thank you.
Okay. So in this like code, we are trying to like fetch the California housing dataset as pandas data frame. So let me briefly like print the what is inside this dataset. Okay, so we see that like there are 8 columns. Like we have, for example, like a median of a block group, or like income of people, and also we have like house ages. We have also like number of bedrooms, number of rooms, number of like the longitude and also latitude of the like house. And like using these 8 numeric values, we want to predict the average price of that house. We have, as it's stated, we have 20,000 data from here. So we can also like explicitly look at the data. So for example, we have this 8 column over there, like these are numerical values, and we want to like construct the MLP model, multi-layer perception model, that takes these values and tries to predict the median of the house value, like price of the house. But like before this, we can also make extra visualizations. Like we can apply a principal component analysis. This technique is like to reduce the number of dimensions, and also we use it for seeing the correlation between different like dimensions of the PCA output. So for example, we have like, as you have seen, we have 8 columns, but we can reduce it to 5 or like any value so that we can see the like the correlation, and like it will give like my plan is to give you a basic like the understanding of what is the task of a MLP model. So it's going to be like let's say we want to have 4 different components. Like we had 8 and we want to reduce it to 4. Like we have a PCA model and we give this value PCA. Yeah, I think 4. And also, like I have to mention that this like object has 2 different attributes. One is the data, the other is target. Like data includes the first 8 attribute, like which are going to be the input of our MLP model. So the target is the value that we want to predict. As we run it, like we see, yes, like it's like in the first part, it's like the 8 value, as I said. The last part should be the target, but I guess like okay. Let's apply this principal component analysis. We have to, I guess, first like compute the ratio between like each column, so that like we can find like in this way, like we have reduced the number of columns, like the number of columns over there to 4, and we have to find the ratio in between. And I'm just making it like percentile version here. And let me also write 55 plus 1. Our goal is to predict this value. And we have a visualizer. And the one last thing is the variance type as percentage. Okay. I'm just I don't want to see the diagonal entries because the correlation will be highest there because each entry is correlated with itself. So let's see what we will have. Okay. So we see that these are the let's say we have an MLP model and in the first layer we had 8 columns and we had a linear layer, let's say it map 8 column to 4 column and you can see that each column is like this. So like these columns may not be meaningful in terms of human understanding. We had 8 columns previously, but these were understandable in terms of one was, for example, the price of the something, the other was longitude, the other was latitude. But for example, we had as I said, we had an NLP model, and the in the middle of the network, we had um, 4 different channels. So we want our neural network to create such, for example, over this part. I guess we can focus and zoom in a little bit. No. Anyway, we want our neural network to create some patches over there. We want our neural network to create a weight or find a weight such that, for example, this darker area is maps to 0, the lighter area maps to 1, etc. And this mapping also will be from the our input to this hidden state to the output state. So we can basically construct a 2 or 3 layer neural network that applies this transformation. So we can use PyTorch library for this. As you have seen in the previous presentation, we can use an sequential model to combine sequentially different layers, but we can also apply it in a much more wider way. For example, we can write a class, let's say since we have a regression task, we can name our model as regressor. We can state it we can have different linear layers called fully connected because as you have seen in the previous slide, it connects the one layer fully to the other. We had 8 layer input and we had the hidden 24 parameters. We can also use this as a hyperparameter. For example, we can state h1 hidden and we can put it over there, h1 hidden, and this may be 24 by default. And we can have another, let's say fc1, fc2, h1 hidden, and this can h2 hidden, let's say. Let's say we want to have 4 different layers. This will be the output layer, and we know that this will be 1 since we are doing a regression. Oh, this will be 3, 2. Stage 3. Okay, then let's say this is like we can like divide this number by 2 at each time. For example, we can start on 24 and like go below to 6, and we can have 1. Since these transformations are linear, if we don't have any activation, any nonlinearity function, like there is no meaning of having more than one layer, because it's like multiplying 2 matrices and you will end up with a single matrix. So that means that to have a much more capable neural network, we have to have also an activation function. This can be a rectified linear unit. This function is like if its input is positive, like it doesn't change its input. Like let's say we have input. If input is positive, it doesn't change it. But if it's negative, it like cuts it with 0. So this will add some nonlinearity to our neural network, and it will be much more capable. To define its forward pass behavior, we have to have like a function called forward. At each time, for example, we had the input. These are the 8-channel input. Like we want to predict its output, so we will apply fully connected layers one by one, and we will pass every time the output to the activation function. So this is sometimes called a linear block or dense block. Like to have a better understanding, we can keep that separate. This is the last layer, and you want to like output it FC1, FC2, FC3. Like this is the full definition of our neural network. Like it will be like net regressor 24, 12, 6. This will define the hidden parameters. Like we can also like apply many tests to predict these values. And also this definition is equal to, like if you want to make it much more compact, for example, in a linear 24, 824. So we can like define it in that way too. So let me finish this definition. I guess. Six and so these are like equal in terms of capabilities. So people like may prefer this network or that. But if you want to have, for example, a neural network that is not sequential, for example, if you want to add, for example, output of the first block to be like passed to the last network, like if you want to bypass the second and the third layers, you have to use much more explicit form instead of just making it with sequential. Let's run this script. And let's see the output of this definition. Like let's have like print our neural network. Like we expect to see such an output. Okay, like we have all modules that are like listed one by one. In this version, it's much more maybe explicit. You can see the sequential line, for example. You can see all rel layers that are in between. But I said like it's a design choice. It doesn't change the like computational power of it. This is like up until this point we have defined all the forward paths, and also we have defined how we can compute this problem. For example, if you have let's say what we have here, we convert it to numpy, and also we want to check the shape. We take, for example, one sample, like the first element. Like this is a typical input that we will have, and let me show you what we can do with this network, with this data. Uh, Okay, like we have applied unsqueezing because like in neural networks we handle a batch of data instead of a single data. So that was a necessary part to do. Or we can like apply it like this, which will take it as a list, so we don't need to unsqueeze it. And for example, this is like network. This is, let's say, our input X, and we passed it to the network. I guess, yeah. Like NumPy, like here is the part. Like NumPy uses float, like double is a float, but Torch uses like 4 bytes. Torch NumPy uses 8 bytes, so we have to apply a conversion. I'm not sure if we have imported NumPy, but we can do it there. Okay. Like this is the expectation of our model. So let's see what was the ground truth of it. We don't need to do the conversion, etc. First, let's print it as well. As you see, they are so much different from each other, and we want to have a like optimizer, like to iteratively solve a minimization problem, which is the error between like the ground truth value and also like the prediction of the model. Uh, Okay, so to do so we import Forge optimizer. Like we have few optimizers, but we widely use this, I guess, Edim optimizer, and people also use stochastic gradient descent with momentum, but like we can use both. We have a network. We have the constant parameters of neural network, and also we have to define a learning rate. Like like this value is a very typical learning rate value. Let's see what we can do. We can also define, since this is a regression problem, we have a loss function, which is basically, as I said, just the Euclidean distance or Manhattan distance between the input and also the output and also the prediction. So like we have a objective function, which is like, let's say, torch and then functional MSC loss. This is the exactly like the difference between prediction and ground truth. Like, let's say observations. We take the square of each difference. We find the mean, and we apply square root, I guess. So they are equivalent, but I will use the torch version. Okay, we have defined our optimizer. We have defined our objective function. Now it's time to like write a fully implemented training pipeline that like updates our model so that we can have a better predictions. Like, uh, Uh, but the first task is, since we have only a single data, we have to split it into two as train and test, so that we can like train on a separate data set and test our code like to see the performance of it. Like testing with a subset of data that was previously trained is not a good option. Let's see. So I will call X and Y as my target and data. So let's apply. Okay. Like with this code, like I'm just splitting the 70% of the whole training data as train and the 30% as test. Like people typically choose maybe 80 or 90%, but like since we have lots of data, we can apply it like this. And we can also define our hyperparameters, and for example, number of epochs as 100. This is like each epoch is like the number of passes that you pass through over all the data. We split our data into batches, but in each epoch we iterate through all batches. So we have to define a batch size. Maybe like people choose like this value as between like 8 and 64, like depending on the task. Uh, but this like having a lower batch size gives you a nice stochasticity of your model that like you can have a better convergence. Uh, this is a feature of PyTorch. Like you have to set your neural network like as test mode and also train mode. It looks like it's evaluation mode. Like this command lets your neural network to for example, if you have um, batch normalization, for example, or like dropout, this train commands like lets them know that they are like reading a train data because like you don't change, for example, the values of like hyperparameters of batch normalization during evaluation. So it's kind of needed. Uh, let's say we also want to um, I guess like before that we have to do something a conversion. Like we had these are, as you have seen, these are like data frames. We have to first convert them to PyTorch tensors. Uh, um, and also we can like train it in this way, or we can also decide to like write it like as a much more structured version. Uh, we can write a data set script that handles those things for us. Uh, like we are writing a wrapper at this point. For this wrapper, we have to build two functions. The first one is the length of the dataset. So let's say we will take something as data, which is going to be on the data frame. So we can apply all these things inside here. Okay. Let's say we have X and Y here. So the length of the data set will be either the length of X and length of Y because we assume they have the same length. So let's give this one. Like this, the get item is for accessing. Like you want access, for example, like the indexed item. So let's do this thing and move them to here. We have training dataset, which is the dataset that contains train train, I guess. And we have also a test dataset. And y test. Should be something like this, but I guess like the problem is that since we used the data for the previously assigned value, I guess we had a problem, but like we can solve it by starting from scratch. Okay, so let's see. All right. So let's run them all again. We have a train dataset. We have also a test dataset. Let's see their length, for example. Okay, when you apply this command, like it goes to there and it gives the length of the X, like for example X train and also X test at that script. And we have also, as I said, get item. Let's see what we have with get item. Let's say we want to get the second index value. It's a tensor. Let's see its shape. Oh, it's a tuple. Yes, because like it's a tuple because we have an input and also output. Let's see the shape of the input. Like it's 8 as we expected, and here will be, it should be 1. Oh, yes, it's a singleton. So, for PyTorch, we use what is called a data loader to load these data sets into batches, like with a quick way. Let's use our implement our data loaders. Like here we define our batch size over here. Maybe we should put it above train, like train loader script. Okay. So we have X and Y. Data loader. Like like let's see if it will work or not. Yes, it's working. Like as we said, like we have defined the batch size as 10. Like data loader like reads 10 times using get item and like combines it, concatenates it, then like gives here. What are we going to do is like as I have shown, like we have to find the prediction of our neural network. Like we have this neural network. Like let's maybe like we can pre-initialize it over here. We had like we had our neural network, we have optimizer and objective function. For example, I have like I assume that this thing will work. Okay. So as I said, the error is like the difference between the like prediction and also like observation. So one way to like see it is like basically use our objective function. So let's see listing as item. So let's like for the sake of like simplicity, let's see the value. Like we see the difference like as a numerical value, but as you see like there is no change. Like of course like it's the value is different, but there is no like increasing or decreasing behavior because we didn't apply backward gradient descent application. So to do so is like we start with optimizer 0 grad. Like as far as I remember, like to update the values inside your neural network, it takes like the time complexity of this operation is n squared. But if you like utilize what is called chain rule, like it becomes linear, meaning like the time complexity reduces to n. But to do so, we have to first the zero, or like the reset all gradients because like we first reset it and we apply the backward computation of the loss function. Then we like from like the last layer to the first layer, we compute the gradients using chain rule. As you remember, like we had implemented the forward pass in the neural network, like thanks to the autograph function and what is called automatic differentiation. The backward is already implemented for us. When I apply optimizer step, this thing will like update all the parameters as it took the parameters here. Let's see. We don't print anything. Like we can also define a list using a garbage space from Torch. We can take like the length of this thing. Like we can take the batch index from here. We can also enumerate so that we can see the like the error. Okay, so maybe like every time we can reset it over there, and we can print at the end of each epoch. This will give us the error over a batch, like over all batches, like the expected error of an epoch. So as we see, like there is a change, of course, like it decreases as our optimizers works well here. So maybe like we can also see in a plot like this time we can like take the number of epochs element, and every epoch we can like set it there. Like, let's run this thing. So like we have a small warning here. It says that like these shapes are different. Okay, yes, these shapes are different. So, but what we can do is just we can maybe apply an unsqueeze operation. Yes, they are the same right now. Okay, there is no error or warning. So let's plot our loss curvature. Yes, we see a sharp decrease. Like we can like change the parameters, like for example, number of epochs, page size, or also learning rate to find like a much more suitable performance. But I guess this looks like a very nice behavior. Okay. Like we can also like what else we can do is like we can also like train this model using GPU, because like even though this model was so much simple and like we could be able to train it on CPU, we can apply CUDA transformation. Like it will like map this model from CPU or to CPU memory to GPU memory. But to do so, we have to also apply this transformation for dataset as well. I'm not sure if we can see any difference for such a like short neural network, but like assume that we had a very like heavy and dense neural network having lots of parameters. You would definitely need to do so. Let me also import Torch summary. Uh, like first check if we have Torch summary. Yes, we have. This is a way to visualize your model. I guess this is just net is enough for input size. I guess it's 8. Should be couple. Okay. So this shows like, for example, we had like 600 parameters approximately. This is the model that we had. And it basically shows that there is no like complexity in it. And lastly, what else we can do? Like we can also apply like the testing or evaluation. Since we have split our data set into two, we can also like see the performance of our model on test data set, because this curvature like is not showing anything. Like we don't know if the model is really learning or overfitting. So one way to check it is like apply it on test data set. In test dataset, we don't have epochs or something. But before that, like, let me show you a difference. For example, let's have a, like, we had an input x. Like, this requires graph parameters check if this model is differentiable right now. or not, because when you apply this backward transformation, it starts like it creates a graph, like a computational graph, and it computes it in a backward notation way, and it applies this transformation to all parameters that require gradients. But this x doesn't require graph. Let's check also y. It doesn't require graph as well, but y pred, let's check this y pred. It requires graph, which means that when you when you pass the input through network, since the parameters of neural networks are differentiable, like y pred becomes true. So we don't we stop at this point, like computing our graph. We stop at this point. We don't update, and we assume that these are the leaves in our computational graph. But for testing, as you may expect, we don't want any updates, so we also make sure that these values, all of them should be false for testing. To do so, we apply torch no graph operation. Within this with block, every operation will not require any gradient. So let's move on to this application. Let's say so we have this data set. Let's also have this thing. You will not have curvature. Since our neural network is trained on root mean square error loss function or MSE loss function, we write the MSE result only. We could have we could try different loss functions, but this is also a logical idea. Of course, you have the rid of this. Okay, so you can also check at this point that if they require gradient to make sure that, as a sanity check, for example, as you see, they don't require any gradients. Okay, so let's put it down there. Okay. Let's see the last element in our loss curvature. We can also basically print it. So we see that the root mean square error on the training data set was 1.7, but this time 1.6, which means that we didn't memorize anything. We didn't overfit to the training data. We have a model that learns it very well. Okay. So let's quickly move to the other example. This is for classification. We have also what is called this one was regression. We have also classification. This time we will use a publicly known dataset. This dataset is widely used in computer vision area. And this is called CIFAR 10. And okay. The Torch Vision is a computer vision library for PyTorch. It includes many implemented neural networks and also their weights. Like people like publish their codes, like they show their architecture. For example, we have AlexNet, ImageNet, ResNet, many different models, and we can see their model here. For example, we have AlexNet, ConeNet, DenseNet. These are, and their weights are also publicly available. We have also data sets over there. Like we have CIFAR10 and all other data sets. These are mainly for classification, I guess. Like we start with writing a transform. This transform composes like NN sequential. We try to we sequentially apply each transformation inside here. We are doing transform because we don't want to we will not have a chance to write where is my data set? Yeah, we will not have to write such a data set. This transform is when you pass it to the data set, it's applied to each sample here. Like if there is a transform, they apply it like this, maybe, and then they send it to the input. So we define that let's do these operations, then send this data to the data loader. The first thing is of course, to convert it to tensor. Then since the CIFAR is like not normalized, we have to first apply the normalization. This is this something that we can find from its its website, I guess. So let's again, similar to our previous example, let's define the batch size. We have to using PyTorch, as I said, Torch Vision. We have to install this dataset. It's as you see, I have previously installed it, but these are the parameters that are defined for CIFAR10. They decided to implement it in this way. Okay. I guess this is all for train data. We can have a look at the source code, and I assume that we will see something similar to what I have implemented for regression task. Let's say, let's make this false. Let's also do train data loader. We have defined our batch size here. For training, we shuffle the training data, but for testing, it doesn't matter because we are not applying any stochastic application. If our memory allows, we can even send it as a single batch. Let's see. As I have installed, let's rename this and see what will happen if you are doing in the first place. As you see, it's just downloading this CIFAR from to University of Toronto, and after that we are done, I guess. we have to also define some classes. These classes are also like coming from the authors of this dataset. So let me copy and paste. Like in CIFAR 10, which means that we have 10 different classes, and these are there. Like we have plain. Like I can also show you the website of this dataset. Like as you see, these are very low resolution images of 10 different classes. Like I will try to like make them visualize so that we can see, and we will see that they are like really low in terms of resolution. Let's like visualize it. I don't know their format, but we have to, I guess, first apply the unnormalization because we have already normalized it. Like this is an Python image object, and we are transforming to a NumPy object, and we have okay. And the last thing is that. So let's take a batch from a training dataset. This is actually what happens when you put your train data loader inside the for loop. Like these are equivalent. So I'm just applying a quick trick. Oh, we can just do this thing because a batch is just an image and labels. There is a like utility function of PyTorch vision. Like since we have defined our batch size to be 4, like we will have 4 images here. They will make a grid from the image. Okay, let's see if it will work. This is intro. Yes, like we have possibly a truck, a frog, a dog, a cat, but let's see if they're so. Let's say like since we have defined our classes over there, like we can like let's see our labels here. Like these are probably the locations, like the indexes of these labels. So to like to see the annotations of it, like let's do. Okay. So like since we have the shuffling, like let's like just apply the test data set to see the same images at every run. No. Okay. Like we see that we have a deer, a frog, a cat, a sheep. But as I said, these are very low in resolution. But this is like, I guess, not a problem for a like neural network. And like we will write a neural network that tries to like what is called it classifies it basically. And let's put it there. Okay. So again, like we start with like a CNN and NLP combined model. So this time I assume that like we can apply it with like we can like write a code with sequential, but I guess maybe it's better to like write it explicitly. We have this thing, we have Torch NN is basically like a wrapper like includes wrapper objects for this functionals. For example, we have fmsc loss, which is a function. We have its wrapper as like msc loss, which is an object, or we have relu, frelu, which is a function that computes the relu as I shown you previously. We have also its wrapper class. This is I guess for like defining object properly, but both of them works. Like we have a classifier. This is needed to initialize some module properties, like it defines parameters, buffers, etc. Otherwise, we will get some error, like without it. Uh, okay, so this time, since we have an RGB image, we start with, instead of 8 channels that we had in regression, we had 3 channels, like these are red, green, and blue. And we, like, in the middle layer, we will have 6 different channels. And we have a kernel, like in the convolution operation, we have 5 by 5 kernel that iterates over the input to obtain such an output. Technically, we have 6 different kernels. Uh, like each kernel like maps to a single channel. So at the end, we will have 6 different channels. And we have the max pooling, I guess. This is a 2 by 2 max pooling. Like it, this is for reducing the dimension because like even though this is a low resolution image, in many tasks you have to reduce the number of parameters. Otherwise, like, we have to update so much parameters. This max pooling basically like reads 2 by 2 patches and takes the maximum of it. So the gradient will be passed to the maximum element. The other 3 elements will not have any gradient update since they are not contributing to the value. Again, we start with this thing. We had 6 dimensions. Let's increase it to 16, let's say. And like this was the CNN part of the neural network. We have to flatten it because it includes like convolution is operated on 3D dimensions. We have to like reduce it to 2 dimensions, where the first dimension is the batches, like batch of images. The second dimension is the features in each image. So we will apply a flatten operation, but like it's not defined as a wrapper in NN. So we will do like a functional thingy. So this will be 16 channels, and I assume that it will be like something 5 by 5, but we will check. Okay, let's see one and then linear. So let's like our goal is at the end of this neural network, we want to have 10 different outputs. Each will like give the like the probability of like given that image, what is the probability of this image? Like this image belongs to a class, for example. Let's like these numbers seems like magical, but like there is no trick. We can like change it as we wish. For example, we can set like 15, 14, let's say. 40 is a good option, I guess. So as you see, we don't have any nonlinearity. We will define it as functional. We will first convolute this neural network, and then we apply the activation function. Then we will apply pooling. This will be a block, a convolutional block. We will have another convolutional block. Then after a while, we have to like apply a flatten operation. I'm not sure if this one is defined, but if it's defined, this means that flatten it accepts like flatten means like have a 1D array, but we want to have a 2D array. So this will ignore the flattening the batches. So this is what we expected, but we will check. Let's see, 1x and so this is a linear block as we have seen in the previous implementation. So let's have our classifier here and also like visualize it. Like let's also show the shape of the image. So we will have 32 by 32 image in CIFAR dataset. So it will be the input of torch summary. What's this thing? What is the problem? Oh, like which means that input is in GPU, but the weights are in CPU, which creates a problem. We can either convert we can either define the device as CPU. I guess this will work. No. Huh. Okay. Again. Yes, this will work. Or we could also like pass this device to CUDA and define the device as CUDA as well. This would work as well. But it takes a little bit time in the first place, but in the second run, as you see, it's faster. Because it I guess caches in the GPU in the first place. So you see a little bit change here. We have much more hyperparameters. Instead of 600, we have like almost 60,000 parameters, which means this model is much more capable of doing something. So let's not spend time and like apply everything that we have implemented. We can just take it from here if you like, because like what is good with these architectures is that they are widely transferable to any problem. So let's say we also we have an optimizer. Optimizer is again hidden test parameters. Let's say this is one of my testing. Let's say. But since we have a classification problem, we cannot use a regression objective function like mean square error, etc. We have to use, for example, cross entropy loss, for example. Okay. Maybe this is much more parameterized. Let's see if it will work. Looks like yes. Since we will have so many like batches because we defined it to be 4, let's like we can just print the loss curvature at the end. Maybe. Since we have a much more complex neural network, it takes a little bit longer time to train, I guess. But I assume that it will not take so much time. This is, by the way, its performance on CPU. We can also apply the same thing without changing anything, like on GPU, to see the difference or like the time that it takes on both CPU and GPU. Okay, like it seems like it has finished. And we can even copy our script from here. Like you say, there is a slope, but like it feels like we could do it, like we could much more optimize it. Like the reason why it doesn't have any like a plateau like we had here is that we had like the first thing is problem is a little bit much more like a little bit more complex, and also we had the less epochs that we passed through over the data. Let's see. Not testing, but okay. Like, let's pass it to GPU device. Or let's stop it instead of waiting that much of time. Like, let's if index is like since these are starting from 0, we have to like edit 1 to make it like human understandable. We have also plus 1, we have also like this thing will give us a particular loss. And also we can also like print the loss over an epoch like this. Sometimes people add like some profilers. For example, they also want to measure the amount of time, for example, the data load that takes to like prepare this page, and also they apply it for forward and backward passes. They then like optimize their models. So we see that there is like since we can have such increase, we also train it with still two epochs, I guess. Like we will have again similar behavior. I have previously like uh, trained it with 100 epochs here. Like because like we can also see its behavior in 2 epochs, but let's see its behavior in 100 epochs. So like we can directly copy this script from here to like let's say we had I guess underscore over it. Test data model. This is for like seeing like the performance of our model on the test dataset. Oh, maybe this thing will work. Okay. So after 100 iterations, like we see that like since even like understanding what is a little bit hard, but I assume there is an animal. It's either a mice, uh, or a cat. But as we see, like the prediction of our neural network is we can predict, for example, like this is exactly the result of our model. As you see, like these are the ground truths. It's cat, ship, like another ship, and we have also a plane. Uh, this is the result of our neural network. Like it, as you see, it mispredicts the first and also the third image. It assumes that to be a ship, and this one also a ship. We can also apply this like testing pipeline, which is not different than what we have did with regression. So we see that we have an accuracy of 55%. We can also like do this with what is the problem? Like since we have 10 different classes, we can also apply this test for each class separately. Like we can measure the performance of our model on test, like on let's say the plain classes, because like it may be the case that we have a imbalanced data set. As you see, like the predicting cats and birds are like, and also there is harder than like predicting like ship or a car. Uh, so this is also a challenge, for example, in neural networks. Uh, I guess like we are like finished the implementing a regression and also classification model. I hope like you enjoyed and also like learned something. I really love to like answer your questions, and I will I guess share these files with you. We have also the final versions that I assume, and we have also the implementations from scratch here. So thank you for listening. I guess we finished it just on time, I guess.
In the meantime, maybe we can receive the questions if you have any.
Okay, let's talk. do we have, in the meantime, okay. Seems like we have no question, right?
I guess so.
Okay.
We have one question. But check. What do you recommend for fine-tuning the hyperparameters?
Especially like this is like let me present my screen again. People use either grid search or like Bayesian analysis, but I recommend like there is a website, WMB. Like this WMB allows you to like apply. For example, this is my research for hyperparameter search. Let me see the control of this thing. Overview, yeah. For example, like what I recommend is like you can define your neural network, like or the whole pipeline as parametric as possible. For example, we have the hyperparameters of conditional random field. We have 5 different parameters. Like I have defined instead of like setting rigid values, I have defined them as uniform distributions, and like I have applied a Bayesian parameter search. This is a widely used approach, I guess. Like people prefer to like, especially in this website, because this website, for example, shows the like the correlation between each hyperparameters. So if you write your code instead of like on a notebook file, if you write it on a Python script, and if you run it via this website, for example, this is like a very good visualization and also like application for hyperparameter search. And also like you can also define a grid search as well. People make tables, for example, using grid search. If the data set is too large on the model without downloading the data. In some competitions, people prefer to like they, instead of just giving you the data as it's too large, they want you to write a model, an architecture, let's say, or the full training pipeline that will work on the data set. For example, instead of like the you to download everything. This is one way, but I don't think that like without downloading the data, like if you don't have any access, like I guess there's no way. But people, as I said, like prefer not to share sometimes their data instead of being too much or too large.
Do we have any more questions?
You're welcome.
So I would like to thank everyone for attending our workshop. And so I would like to thank to our lecturer, Adnan Ardoğan, for his valuable contributions. So see you in next meeting, next event. So we have an upcoming event on January 23 to 25. I sent the link via chat. So please check if you are interested in quantum machine learning.